You guys can take it away.
Awesome. Thanks so much, Albert. Isaac, it seems like my connection is a bit unstable, so if at any time I disconnect, please take over. But let's see here. Can everyone see this?
Yep.
Okay, awesome. So welcome everyone to our Mastermind workshop, where we'll be teaching you a little bit of the algorithms that you can use to intro to your first AI algorithm. And I see there are over 30 people here, so that's really good. Let's see. Okay, so first of all, a little bit of an introduction of who we are. So Isaac and I are both PET alumni, and we both went to the University of Waterloo for our undergrad in mechatronics engineering. I'm currently studying computer science for my master's at USC, and I'm also currently working at a startup called Dragonfruit AI as a software engineer. Isaac.
Yeah, and I'm Isaac. I'm currently working as a software engineer at NVIDIA on the robotics platform team, and I'm also a graduate from mechatronics engineering at the University of Waterloo, and a PET alumni. So that's cool.
All right, so the goal of this workshop is to basically not specifically learn about this one thing, but get you in the habit of being able to understand a new CS concept, implement it in the language of your choice. And in this case, we're running the workshop in Python. And then a little bit about cleaning up and optimizing your code for readability and also efficiency. And we're gonna go a bit fast because we have a lot of slides, and we'll try to get through as much of the content as possible. But if in the future, even after this workshop, you guys have any questions, we're available on Discord for you to ask questions, and we'll get back to you as soon as we can. So before we get into the nitty-gritty of the software, what is it we're trying to do here? So what is the game of Mastermind? I don't know how many of you are familiar with it, but essentially it's a very simple game. The game of Mastermind goes like this. There are two players. There's a code maker and a code breaker. The code maker would create a secret code comprised of 4 colored beads, and the game has 6 different colors available. And you can have multiple of each color. So you create a secret code of 4 beads, and the code breaker's job is to figure out what the code is. So code breaker would put down a guess as a row, first row here. And the code maker will look at the guess and respond with these black and white pegs. A black peg signifies that there's a correctly colored bead in the correct position. And a white peg represents a correctly colored bead, but in the wrong position. So let's just go through 2 examples here, the first 2 guesses. Here, the secret code is blue, green, black, and red. And the code breaker guesses white, blue, yellow, green. Now, they're now getting a response of 2 white pegs, which means 2 of these colors are correct, but they're both in the wrong position. And we can see that it's coming from the fact that there's a blue here and a blue here, and a green here and a green here. Taking in this response, the code breaker then guesses a second time. This time, he gets 1 black peg representing this blue bead over here, which is in the correct position, and 2 white pegs representing the black and red, which are just flipped position. And so the code breaker wins if they're able to correctly guess the code by the time they hit the end of the board, and the code maker wins if they're not able to guess it. And we'll make this slide available to you. So I guess, Albert, I'll give you the slides afterwards so that you can distribute it if they, so that everyone who wants to participate can refer back to it. So here's just a summary of what I said before. In our game, we'll use 20 guesses as the maximum. So how would you participate in this workshop, or this challenge rather? We will be giving you a Google Colab file. Let me see. So just to show you, the Google Colab file will look something like this with some boilerplate code and some stuff that I'll be running through with you beforehand. But essentially, we want to make it a challenge where you write your solver for Mastermind, and then we'll put you on the leaderboard. And podium places will receive Amazon gift cards, and also you guys can get some time with us as like a coffee chat where we can connect you to anyone who fits whatever current goals you have in the world of computer science, whether it's a company you're interested in, or whether you're interested in startups, you want to connect with people, we can help you do that. So yeah, some incentive to participate. So in this activity, Isaac and I have created this Mastermind class that will play the part of the code maker, and you will be making the solver class, which will play the part of the code breaker, repeatedly taking guesses at what our secret code is, and we'll give you the response of the number of black and white pegs, which we will give to you in the form of a tuple. But before we go into the details of that, we'll go through some key Python concepts with you that will help you through the challenge. And Isaac will lead you through that.
Yes, I will. I don't think I can control the screen, but I'll just let you know, Jullian, when I want to go to the next slide. So there's a few data structures that we want to cover. We know that there's about half of you that probably already knows all this stuff, but because the other half might not, we're going to cover all our bases and just through these data structures. I want to, start this off with saying that there's by no means the stuff we're saying here is comprehensive. If you guys really want comprehensive syntax on how to operate on these data structures, it's all in Google, so you can just Google it. I have some links at one of the slides further down. You guys can look through for that. So yeah, let's start. Jullian, next slide. Cool. So we're gonna start with lists. So lists, as I understand, the beginner side of the class learned last week. So it's basically just a way to store a sequence of variables. Whatever those variables might be doesn't really matter. It can be characters, it can be strings, it can be integers, floats, whatever. You won't really have to worry about variable type as much in Python because it's dynamically typed. But we have a few examples of how you would initialize a list up here. You use square brackets and you specify each element with a comma in between. And you can also specify an empty list, which is exactly what it is, just an empty list that doesn't have anything inside. And if you try to print it, then nothing will be inside. So if we move to the syntax for appending or adding something to a list, this is the syntax to add something on the end of a list. So you can see that I added in the order of 1, 2, 3, and when I printed it, it shows up as 1, 2, 3. Cool. Yeah, and then there's also something else that's important to know about a list is that it's ordered, and you can refer to things by indices. And it's important to bring this up because the next data structure we're going to go over is sets, which doesn't have those things. But because it's ordered, you can have duplicates. So you can add like 2 1s or 2 3s or 2 apples or 2 A's or whatever. You can have duplicates of variables. So the next syntax we're going to go through is inserting an index. Sorry. Go back.
Yeah.
Inserting an index, which is exactly what it looks like. You insert at index 1 or 2. It's important to know that lists in Python are indexed at 0, much like every other language except for MATLAB. So, I insert at 1. So it used to be 1, 2, 3. Now it's at 1, 4, 2, 3 because the index of 2 is 1. And so you inserted 4 into it, and then everything was shifted right. And if you want to access an element, then you would just take the name of the list and then use square bracket and specify an index. Next slide, Jullian. Cool. So removing things from a list, there's 3 methods to remove. There is removing from the end of the list, removing from a specified index, and removing a specific value. The syntax is there. Pop is to remove from the end of the list. It goes from, the example on the right, 142 to 12. From a specified index, I specify an index of 1. So in the list 1, 2, 2 is at index 1. Oh, wait. Well, yeah, so it pops at 1, so you end up with a list of 2. And then when I remove specifically for 1, it'll remove 1. So I just end up with a list of 2. And then there's a few helper functions to get the length and count of a list, which I'm going to explain here, which will be useful in the challenge. Len, when you use the function len and you pass in the name of your list, you can get the length. So it was 2, did 1 and 1, so now there's 3 elements, and when I look for the length, I get 3. And then the count function, the dot count function, counts the number of one type, like one variable inside your list. So if my list has 2 1 variables, then it'll return 2, which is what it did here.
And if at any point anybody has any questions, please stop us. Yeah.
Cool. So the last thing we want to talk about for lists, because it's used in places in the code, is something called list comprehension. And it's actually not as complex as it sounds. All it really is a simpler, shorter syntax for creating lists. So instead of like, you have an existing list of fruits and you want to create a new list from it, let's say a list that has everything that fruits have, but only for, fruits where there's an in its name. Instead of, writing a for loop to do that and appending it onto a new list, you can write it using list comprehension. And it'll be a lot simpler in the Python syntax. And you'll notice that it looks a lot like pseudocode. It's because Python's pretty close to pseudocode. Yeah, so as I said, a list with only A's in the name, so you get apple, banana, and mango. Next slide. So the next data structure we're going to look at is sets. And so sets is also a way of storing a sequence of variables with the unique property of being able to distinguish duplicates. And it can do this with a pretty good efficiency or time complexity. And I'll explain why or how this is used or where this is used actually in 2 specific functions that we're going to use for sets called union and intersection, which is pretty important to the challenge, but it's pretty easy to understand. But anyways, so getting back to a set, it's initialized in the same way as a list, except you use curly brackets. So pretty straightforward. You can put in any type of variables as well, as long as it's hashable, which will be explained later. But I started a list of 1, 2, 3, and you can see that when I print it, it says 2, 1, 3. And that's because it's not ordered. So variables in a set aren't indexed, so you can't like refer to one. Like every time you refer to, I don't know, like the first variable in a set, it won't necessarily always be the same because it's not ordered. And you can't refer to things by index. So the syntax for adding stuff to a set and removing stuff to a set here is just .add and .remove. I added 4 twice to show you guys the functionality of a set. So, initially it had 1, 2, and 3, and I added 4 twice, but there's only 1 4 that ends up in a set. And that's because the second time I add 4, the hash was able, the set was able to distinguish that it's a duplicate and it doesn't get added. And then remove, you just specify the variable name. So I remove 1, and now I'm just left with 243. Cool. So these are the two functions that we'll use in the challenge. They're called union and intersection. So first, we're going to start with the union. So union is basically the function where if you want to combine two sets, but only keep the distinct elements in all the sets. So an example of this would be, if A is a set of A, C, and D, and B is a set of C, D, and 2, well, what are the distinct elements? There's a duplicate of C, so you only keep one of the C's. There's a duplicate of D, so you only keep one of the D's. And you have A and 2, which are both distinct. So if you did A union B, you'd get on the side, you'd see 2A DC. This logic extends to the rest of the examples. If I did B union C, you can see that 2 is repeated, so I only take it once, but all of the rest are distinct, and so you end up with a set of 1, 2, 3 D C. You can also do union with multiple sets. The same logic applies. This is more, you might think like, why can't we just do this with sets? Like, why doesn't set have like, why can't we just do union with lists? Why do we have to use sets? And you can read more on this, online. I'm sure it's there. But basically, like the implementation of set in Python or any language, like gives way to a more efficient implementation of a union intersection function. But all you guys really need to understand for implementing this challenge is what union is, which is just taking the distinct sets, distinct elements in one or two or more sets and making it a new set. Next slide. Cool. So intersection. So intersection is kind of like the opposite of union, but I like to think about it that way, but it's not really. So it's basically, instead of taking the distinct elements between two sets, you take the ones that are common only. So A and B here, you can see that 2 is common between A and B, and 5 is common, but 3 is unique to A, 4 is unique to A, and 100 is unique to B, which means that when you take an intersection of A and B, you would only end up with 2 and 5. And that's what you see on the right here. And the same logic applies for all these other examples. B intersection C, the only common element is 2, so you just get 2. Next slide. So the last data structure we wanted to quickly cover is dictionaries. So dictionaries is also a way to store a sequence of variables, except dictionaries stores something called key value pairs. And it's really useful in certain situations, like let's say you are, I don't know, making a shopping list. And you want to list down the items that you want to get, and then the number of that type of item that you want to get. So like, I want to buy 3 apples, 20 oranges, and 4 bananas or something. And so this dictionary up here would be the perfect data structure for that use, because I have the key of apple referring to a value of 3, which represents like the number of apples that I want to buy. And there's a lot of like other use cases of this in programming in general, which is probably why like dictionaries is a pretty popular data structure, especially for making certain algorithms more efficient. So it's declared also using curly brackets, but you specify key value pairs for each variable, like slot. So apple, and then apple is the key, and then colon, and then 3 is the value. So that is one key value pair, and I specified 3 key value pairs here. So if you want to add an additional key value pair into your dictionary, this is the syntax for it here under the add comment. You would simply use square bracket and then specify key and then make it equal to some value. And then you can see that when I print my dictionary on the right, lemon 5 is now added to the dictionary. You can change key values that are existing in the dictionary. Dictionaries are modifiable. For example, I changed apple to 70. And you can also remove key value pairs by simply specifying the key. Yeah, next slide. So there's a few different ways of looping through dictionaries. Even though dictionaries are not ordered like sets, they can be looped through because they're still like a sequence of stored values. One point I wanted to note is that you can't like when you're looking for something in a dictionary, you can never directly refer to something using its value. And that's because values can be duplicated across different key value pairs. So like, if I wanted to buy 4 apples and I wanted to buy 4 bananas, the value is the same. So if I'm trying to refer to 4, I won't know if I'm referring to apple or banana. That's like in my opinion, that's like the intuitive way of why that is. There's a longer explanation of why that is in the implementation of a dictionary and how hashing works and stuff. But at this point, it's just important to understand that when you refer to key value pairs in dictionaries, you refer to keys. And keys, much like elements in a set, are unique and can't be duplicated. So yeah. So looping through, you can loop through by keys or values. The syntax is here for you to see. It's basically a for each loop in Python, except for the list. You would specify dot keys, which returns like a list of all your keys, or dot values, which returns a list of all your values. You can also loop through by both key and value with the syntax at the very bottom. I think my dictionary.items returns a list of tuples, but yeah, you can do that if you would like. And you can see when I print key and value, they print both my key and value and all my key value pairs. Next slide. So now that we went through all the data structures, we just want to go through one last concept, and that's the idea of nested data structures. Because having one list is fine, and having one set is fine, and whatever. But when you can nest like a list within a list, it's really useful for certain representations of data. For example, if you're trying to represent values in a grid or something, or a matrix, you can specify that as a 2-dimensional list or a list of lists where each sublist is a row. So you can see I kind of typed it out in a square form here at the top. So 1, 2, 3 is the first row of this grid. 4, 5, 6, the next row. 7, 8, 9 is the next row. And this data structure can represent like a 2D grid. It just shows the idea of that you can put lists within lists. And you can actually go like even like however many layers that you want. Although there's obviously you'd have to use the proper setup for whatever application you're using or whatever application you're designing for. And you can append a list onto this list of lists as well. So I appended 10, 11, 12, and now it has a 4th row of 10, 11, 12. And there's also important to note that even though all my sublists here are the same length, that's actually not a requirement. It doesn't have to be like uniform. I can add a list of a sublist of a length of 10, and it'll just end up with like, I mean, it won't be a valid matrix, but like it will be totally valid in Python. Yeah. So nested data structures for sets. So you guys might want to think like, oh, like let's just extend this idea to sets. And so I wanted to include a slide on that. So I basically did the exact same thing that I did for lists, but I did it for sets. And I got an error. And the error is something called it's called a type error. Anyways, the important thing to note is that it notes that that set is an unhashable type. So this is to do with the implementation of set and how sets are able to remove duplicates. You guys can read more on this if you want to know the implementation of a set. But basically, the key here is that not all data structures can directly be nested exactly the same way based on their implementation. Then that's just the note I wanted to send across. I don't think you guys will need to use like nested sets anyways, so it won't matter. Yeah, next slide.
And you guys can read up on the idea of hashing and for future reference.
Yes, yeah, and we included this slide just as an exercise. If you want to, figure out why you can't hash a set and why a frozen set in Python would work. It's not important to the challenge. Next slide. So lastly, nested dictionaries. So dictionaries are nested differently from how lists are nested. But just for, just to be clear, this is how you would nest dictionaries. You would basically specify key values where your value is your nested dictionary. And this way you won't have the issue with sets in the previous example. It's not super important to understand that part, but it's just important to know that dictionaries are nested in this way where you would specify a key and your nested dictionary is actually the value of the key value pairs that you have in your outer dictionary. So like, an example of a nested dictionary would be, if you had like a more complex shopping list, right? And you wanted to categorize between like, oh, okay, so I have a shopping list for frozen foods and I have a shopping list for fresh foods. And then under frozen foods, I have like, beef, chicken, and fish, and I need to buy like however many of those beef, chicken, and fish, and fresh foods. I have whatever foods. That would be exactly what a nested dictionary would be, because frozen foods and fresh foods would be the keys that refer to like the dictionary, which is like the not to-do list, but shopping list for like each type of food. So this is a really simple example, but in the challenge, I think Jullian will later explain how this is used to implement the program. And then lastly, it's classes. So we know that object-oriented programming and all that stuff with classes in Python will probably need a lot more than one slide. And the thing is, to complete the challenge, you guys don't actually need to implement any classes or objects or have a super in-depth understanding of how object-oriented programming works. But we just wanted to cover the idea so like what is this class thing, and why would you, why do you organize the code in a certain way? But as far as like completing the challenge, you don't need to be a master of object-oriented programming to do it. So yeah. So for classes is a way of organizing your code so that it's readable and reusable. I guess that's the most straightforward way of using it or explaining it. It's kind of like, let's say you're making a keep track of people's ages and names, which is the example that is used here. Instead of making like 4 variables where like one variable is the name of the first guy and the second variable is the name of the second guy, and then like 2 variables and then one is the age of the first guy and the other one's age of the second guy. It's instead of declaring all these different variables and then declaring functions for each variable to print out these values, you can organize your code into something called a class, where a class represents a person. And you can give it, classes can be given properties and methods. And properties are like attributes of the class, and then methods are like things the class can do. So like a person can introduce themselves, which we just defined as printing in Python their name and age. And then we can also define the properties of this person, like object, with name and age. And you can see like the example that is given here is that you would create a person object from a person class, and then you create 2 of them, and then just by calling the same function for each person object, you can get the same result of outputting their name and name and age. Yeah, this is a really brief example, and if you guys don't understand why there's a need for classes, it's fine. It's not super important for the challenge, but we thought we'd go over it in case you guys were wondering. Next slide. Cool. So that's all for going over Python data structures. You guys can go to these links if you'd like to look at more comprehensive syntax and explanations of each data type. The syntax we presented here is obviously not comprehensive. So yeah, you guys can search that on Google. Cool.
Okay, awesome. So that was a super fast crash course on basically all of the important parts of Python. And you'll be using some of it in this challenge should you choose to participate. Now I'll just go over some of the things that we're giving you in this Google Colab file. Let me just, okay. So once you open this Google Colab file, which you can then download a copy of here, you can download your own version of the IPython notebook and start writing this code on your own account. And if you have questions about that afterwards, we'll be happy to answer them. But that's easy stuff. So up here, just a preamble on the game and challenge. And then you come to this code, which is actually it's not long. It's just there's a lot of comments here. We have a Mastermind class, which will play the role of the code maker and also be the driver of the game. So you don't have to write, you don't have to write any of the actual system that would run the game, simply the two functions, guess and update, which I'll talk about later. Over here, we first initialize it with a solver, which is going to be an object of your class that you will implement. And then colors is a list of the colors that are available. So as I mentioned before, there are 6 available colors. And instead of using like the words red, green, blue, we'll just represent the colors 1, 2, 3, 4, 5. It's just easier. And then a secret code, which is automatically generated, which you don't have to understand either. Num guesses just helps us keep track of how many guesses your code has, how many times your code has guessed. And guess limit is the maximum number of guesses you're allowed to take before you either win or lose the game. Respond is our function where we take your guess and we output to you the count of black and white pegs. So that's right here. We'll respond to your code with a number of black and white pegs, always in that order, black, then white. And this piece of code you also don't really need to delve into is essentially the process that runs a single game of Mastermind. All you probably need to understand from here is that your code will get called once here and once here. And this is where you will output your guess. And this is where you will receive the response from our side. So what does your class look like? What does your solver look like? There are only 3 functions here that, really only 2 functions here that you need to implement. The initialization phase, it's the place for you to put in any variables and methods that you believe will be useful in solving this game. The guess function returns your guess of of the secret code, the 4 colors. And in the starter code, we give you an example of how you would guess 1, 1, 1, 1. And an update function, which will take in the response given over here. And with this response, you will do something to update your field of search. And that's also an important concept that we have to go over. But yeah, basically the challenge, all there is, these 2 functions. And then you'll run the game, which you don't have to change any code here. You'll just run it and it'll print out the game. And here you'll see that, okay, you took your first guess was 1, 1, 1, 1. You got a response of 0, 0. And since we didn't implement the functions yet, you guess 1, 1, 1, 1 again, you get the same response, so on and so forth for 20 times, at which point you will lose. A finished code for the solver would give you a printout kind of like this, where you take a guess, you get a certain response, you take another guess, a more informed guess, and you get a different response until you win. And if you're to implement the algorithm that we're gonna teach you, you're going to win in 5 or less moves, for sure. Always 5 or less moves. So how do you do that? All right, so I skipped all of that, and we can get right into the Minimax algorithm. So you will be learning about the Minimax algorithm, which is, you can say it's an AI algorithm that helps you with in like multiplayer games, and most commonly 2-player games like tic-tac-toe or chess, where one player is trying to do one thing and the other player is trying to get the opposite achievement. So in tic-tac-toe, one player is trying to get 3 rows of X, or the other player trying to get 3 rows of O's. It's a zero-sum game. It's one person winning is another person's loss. So in that kind of a scenario, the Minimax algorithm helps you to pick the move that will minimize or that will optimize your worst case scenario. And don't worry if a lot of what I said isn't clear yet, because we'll get into it deeper. And for the mathies in the group, here's the actual formal algorithm of formal representation of the Minimax algorithm, but you don't really have to understand it either. And also the content we're presenting comes from this paper by Donald Knuth, who's a very prominent computer scientist. And you can find the paper here. So what is the Minimax algorithm in plain English? Okay, you hit a fork in the road. And if you go left, you could potentially win $100,000 or lose $100,000. If you go right, you could win 1,000 or you lose 1,000. In the Minimax algorithm, our goal is to minimize your worst case scenario. So we would go right, because you would, in the worst case scenario, you would lose less if you went right. And that's exactly how our approach will be to beat Mastermind. Okay, in terms of the mechanism, so the same fork in the road here, think of it as this fork in the road over here, left and right. And I want you all to imagine that these are all blank. So there's no number here, no number here, no number here. So all of these are blank, except at the very bottom. You have values. So think of it as you hit a fork in the road. Over here, you hit another fork, you hit another fork, and you hit another fork. And all you know is that at the end, you could either get $10, infinity dollars, $5, negative $10, $7, $5, and so on and so forth. So you're trying to get the maximum amount of money as possible. But at every step of the way, your opponent will push you towards getting the least amount of money possible. And that's the opponent you're trying to beat. So how would we choose? Not knowing all of this, do we go left or do we go right? The best way to figure that out is you propagate the values upwards. How do we do that? Okay, so down here, you can imagine in a game, this would be your move, then this level would be your opponent's move, this level would be your move, this level would be your opponent's move, and this would be what you would get. So here is your opponent's move. And at your opponent's move, they would want to push you towards the most negative scenario. So your opponent would push you towards -5. Here you have no choice. Here, your opponent will push you towards $5, -$10, $5, and 10. But what you have control over is, do you go left or right here? And since this has a bigger value, you would want to maximize out of your options. So remember, this is your move. You would pick 10. Here you have no choice. Here you would pick $5. And here you have no. Here's your opponent's move again, where they would minimize you. So here's you propagate up -10. Here you propagate up -7. And up here, you are reducing your planning ahead, your decision making to just 2 options. If you go right, your worst case scenario is a -7. If you go left, your worst case scenario is a -10. So you go right. And that's how you would make your computer make these game decisions. Here it will be even clearer because we're actually using tic-tac-toe. And imagine no values anywhere, but instead of money, X, if he wins, that's a +10 score. 0 for a draw and a -10 if O wins. So we are X. So as X, we want to get +10. We want to get a score of +10. We'll look at the situation here. You have 3 different options because it's your turn. You can either put an X here, here, or here, which is why it splits into 3 different options here. Here, your opponent O has 2 options. Therefore, it splits into 2 options here. And at the very leaf nodes, there are no more options, which leads to a very definite endpoint. At this endpoint, X wins. So this square has a value of +10. So you can imagine this +10 here is here. At this leaf node, it's a draw, so it's a 0. Here, X wins again, so that's a +10. Here, it's -10 because O wins. And because over here, there's no split, there are no options, you would simply propagate up, up. So this has this has 0, this has +10. Here, you propagate this upwards. This has -10. And the first time you get a choice is over here. And over here, it's your it's O's turn. And because it's O's turn, O wants to go to -10 as close to -10 as possible. So O would pick this one. He doesn't want you to win. So O would pick this one. And so you can propagate the score of this up here. So this has a value of 0. Now you have 3 different options to choose from. And because we're X and we want a +10, we would go left. Therefore choosing the correct move to have you win right away. What this means again is if X had chosen this move here, it would be in the best if O is a smart player, it would be a draw. And here you would lose. So that's kind of how Minimax applies to the world of games and player games. So now that we've gone through the tree for tic-tac-toe, let's look at what it would be like for Mastermind. And in Mastermind, you can think of it as a 2-player game as well, where one player would take a guess of colors, so say 1, 1, 2, 2, and the other player, the code maker, would play a guess. Would play a move, which is to output the pegs. So this is player 1's move. This is player 2's move. And you can think of it that way as the 2-player game format. So for the first guess, we'll just take a random guess. And for the random guess, it's actually best to pick a 1, 1, 2, 2. So like red, red, green, green, say. And that would minimize your number of guesses. And then you'll get a response of the number of black and white pegs. And at this point, you'll do an update. And I'll explain that later. And for the following guesses, you break out into this giant tree of all the possible guesses that you could take. And this is your opponent's move now, giving you all the possible peg combinations. And the value in the leaf nodes that you'll be working with is how many possibilities are left that could be the solution. Now, in total, there are 1296 possibilities, and I'll go through that right now. So first, update. At this point, after the first guess, you have to do an update. What does that mean? After you receive the black and white pegs, from your record of the universe of possible solutions, you want to remove all the solutions that are no longer possible, given your guess and the peg response you received. So just intuition-wise, if you had guessed green, 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 and you get a peg count of 0, 0, you now know that there are no greens in the actual solution. So a lot of the combinations, green, blue, red, black, green, yellow, white, orange, those are all gone. Those are no longer possible because you're now more informed. So what does that look like? Let me exit out of this and show you. In your code, you'll basically get two different universes. You'll instantiate two different universes. One is the 1296 total combinations of what the secret code could be. And this won't change. It will always be 1296. But you'll also have the exact same set as to keep track of the number of possibilities that are left. Because with each guess, your number of possibilities will start to shrink. So over here, as I said before, if you guess 1111 and you get 20, you now know that 2222 is not a possible solution. So you go through, you basically for loop through all of these possibilities and see what's no longer possible. So this will start to shrink. This will start to shrink while this stays the same. And believe it or not, you will get to literally one possibility within 5 guesses. But to do that, you need to be informed at what you should guess, right? So now this is decreased. How do you now choose, like, what do you guess next, right? And this is where, this is what I'll explain next. But first of all, just in case this wasn't clear, we'll do an example here. So this is not 1296, but here I have a subset of a universe of 6 possibilities. So this column represents this gray circle. This column represents this red circle. So say you guess 1122, but the actual secret code is 4312. What you would do is you would go through all of these possibilities and calculate the response that you would have gotten if this were the secret code. So let's go through that. I guess 1122. The secret code is 1122. What would I get as a response? I would get 40. And I go through that again. So I guess 1122. If the secret code is 2145, I'd get a 11, so on and so forth. Now, you guess 1122 and you get the response from our code, you get 11. Now you know that the only possibilities left out of these 6 are this one, 11, this one, and this one. So already you get rid of these 3 possibilities. And that's how you would do the update. So that's the logic, but you'd have to implement the code for it, which is the challenge. Now for guess. Now that this has shrunk, how do you take the next guess? To take the next guess, okay, so we've done this. We guessed 1122 for the first guess. For every subsequent guess, you can read this. For each possible guess, calculate how many more possibilities would be eliminated for each possible colored white peg score. The score of a guess is the minimum number of possibilities it might eliminate from the universe of possible solutions. Okay, that's a lot to think about, right? But we can break this down with an example. All right, so these ones in gray we already deleted from our update step. Now it's our guess step. To do that, we first build a lookup table or a dictionary. To build this dictionary that we need, we basically do a nested loop of for every code in all, which is here, for every code in all, nested for each code in possible. So your typical for I in A, for J and B, kind of for loop, you would loop through this. So 1122 and 2145. You start to build this lookup dictionary of the code from all, and then the response as the key of the nested dictionary, and a number of possibilities. So I'll show you that right now. So 1122, 2145, we get a response of 11. So here I start to say, okay, I have 1122 as code, and then here is the response, right? So I would put the response down, 11. Of course, this is not hashable. You cannot use a tuple as a key, but part of the challenge is figuring out how you can manipulate this to make it usable as a key. And then this would be 1, because there's now one possibility. And then I look at 1122 and 4312. It's also 11. So now I increment this. There are now 2 of them. 1122 and 1234 is also 11. So I increment this to 3. And then we look at 2145. 2145 and 2145 is 2145 and 2145 will give me a code of 40. And I would increment that to 1. 2145 and 4312 would give me a code response of 03. So this would be 1. And then 2145 and 1234 also gives me 03. So this is 2. And you basically do that for all of these, and you get something that looks like this. Now, this is where Minimax comes in, and it's really easy from here. This is the tough part. So if you understand this, you're like 90% of the way there. The other 10% is this. You will take the max of the number of possibilities as the score of the guess. So up here, you know how we have scores for the nodes, the leaf nodes, a +10 for this one and this one, 0 for this, and -10 for that. We need those scores too, right? In our case. So the max, the score for 1122 is 3. We're taking the max of all the values here. And in the case of 1122, there's only one value, 3. So the score of 1122 is 3. In the case of 2145, there are 2 values, 1 and 2. And you want to take the maximum, which is 2. So what does this mean really? This means that if you guess 2145, at the worst case scenario, if the peg response was 03, you have 2 possibilities left. And of course, we want to shrink it as much as possible. We want it to be 1. We want it to be the least number of possibilities left. But in the worst case scenario, you guess 2145, you get pegged 03. There are 2 possibilities left. And we propagate that worst case scenario up. So now we have all of these. Now the mini part. So we did the max, now it's the mini part. In the mini part, we want to take out of all of these possible guesses that we can make, take the least. So here, if we guess 1, 2, 3, 4 in our next guess, worst case scenario, we have 1 possibility left. Same with 4, 3, 1, 2. So you want to take the min of the guesses. So it would be either 4312 or 1234 because they have the minimum value. And you take the guess with the lowest score. But if there's a tie, you want to try to take one that exists within possible. Because remember, 11222145 4346. These keys are all from all, not from possible. These are all from all. But if you get a choice of whether to pick one from, pick one that's impossible. So in this case, they're both within possible. 4312 and 1234 are still within possible. So either guesses would be good. But of course, as we said before, the actual code was 4312. So there you go. Like, we're very close to that already. So that's the logic. That's the entire logic of what is to be implemented. Does anyone have any questions before we do these last 3 slides, which is going to be quick, pretty quick? Any questions, concerns, comments? Okay. So going through these last 3 slides, Isaac? Wait, you're muted.
Hello?
Yeah.
Can you hear me? Yeah, so to help with the implementation that Jullian just mentioned, we're going to provide some helper functions. So these helper functions are just do the basic things. Here is to calculate the black and white pegs. So previously, Jullian explained how like you score a guess that you made against one of the possibilities in like your all possible universe. That scoring process is basically saying like, you know, if this guess in my all possible whatever universe is actually the correct secret code, then what would the score be? And so there's basically this need for a logic where you have 2 different codes, and you want to get both the white pegs that you would get as well as the black pegs that you would get in that situation. So the first function, black pegs. So black pegs, as you guys remember, is when you have the right color as well as the right position. And so you can see here that it's a really short function with just a for loop where it loops through all the elements inside your secret code and your guess, and then just checks that they match. And then if they match, then you increment a counter. The calculate white pegs function, you don't have to do it this way. There's multiple ways of doing it. But this is a way that kind of like utilizes the num black function to make things a little simpler. But what this for loop does is that it goes through all the colors and then essentially checks the minimum number of matching colors between 2 different secret codes. And so what you would end up is like, let's say that you like you got the correct guess. It would still calculate white pegs would still give you like 4 white pegs. And then knowing that you have 4 black pegs, you subtract that from the number of white pegs you get, and so you end up with 0. So that's the way to do it. You guys can do it in other ways if you want. But these are 2 just helper functions for that. Next slide, yeah. Jullian.
Yeah.
So these 2 functions are just using list comprehension or that type of syntax to basically just do the same thing as we did in the previous slide. You guys can look into it further, but there's a zip function that is used here, which has an but basically, like these 2 lines do the exact same logic as you do above. If you guys want to use these functions directly, that's totally fine as well. But yeah, so they're here if you guys need them. The last function. So the last function is to create like the entire all the possible codes that can exist in your game. And so it's basically like every combination of every color in every different spot. And so normally you can just do that with like a huge nested for loop. But we're just showing an easier example using the product function from the iter tools library in Python. The explanation for the function is online, but basically it's the same thing as if you were to just do like 4 for loops and loop through all the different combinations yourself with all the different colors and all the different places. This is just a shorter, simpler way of using it. Feel free to directly use this function as well to get your entire space of possibilities of different guesses.
Mm-hmm.
Yeah.
So that's basically it. One thing I forgot to mention is, so what we went through here with the update logic, that, just to connect back, is what you would implement within this update function here. So again, this will be available, so you can look back at these slides and kind of think through it again, like, okay, what do I do to do the update? Like, I get this response, how do I do that? So you can go through this example again, and that will go here. And for guess, what we walk through over here is what will be implemented over here. And it's not going to be a long piece of code. Like I don't know how many people are going to screenshot this. The solution is not long. It's that long, and we'll give you the solution later. We just wanted it to be a little bit of a challenge that you can work through over the course of, say, 2 weeks, or if people need more time, 3 weeks. It really doesn't matter. We're in no rush, but just to work through the idea by yourself and implement this AI algorithm from scratch with just pure Python, because Python's a powerful language. So yeah, that was the last comment I wanted to say.